I did not say that. That was not the intention either. Okay, so we're gonna take a look at exam 1, and what I'm gonna do is we'll give this a try and see how that works. Okay, so let's see. Can I convert it into a PDF? Nope, not readily. Okay, I can do it, but I have to. It's kind of roundabout because I can open the document first. Because this way I can kind of mark it up with a tablet. It's just a lot easier that way to show you the answers. Okay, so I can download, because I don't think there's a conversion here that can save it back onto the Google Drive. So I can convert it to a PDF first, which will force it to be downloaded, and then I have to re-upload it back to the server so that the tablet can see it, because the tablet is not connecting to the file system of the computer. So this is going to be a little bit roundabout. Okay, save, and then I re-upload it. I can re-upload it to the shared folder, and we'll just say new file upload from the temp folder. Okay, so it's uploaded. It's right here, and then on the tablet side I can import it. Okay, where did I upload it to? cisp440 shared. Okay, so on the tablet side there's a way to import, so I can import PDF as new notebook and navigate to my Google Drive, go to my drive, cisp440 shared, and it's the last item, and I'm not seeing it. This is a problem that I had before too. For whatever reason, once I upload a file, it doesn't immediately become available. Okay, so let's check recent, no items. It's not seeing that particular file. That is not working. Okay, we'll give it one more try. We'll use the Google Drive app or Google Doc. I don't have a Drive app. Yep, I do. There we go. See, it is on this drive, and we'll download it from here. And then switch back to the other app. Open it from here. Yay. Okay. There we go. So switch back.
Tell me now.
Technology. There we go. Alright. So I can actually write on this now. Last name first. Okay. Alright, question number 1. Okay, so before I talk about the solution, are there any questions about number 1? Does everybody understand what it's asking? Okay, so let R be a relation, and a relation is always a subset of the Cartesian product of whatever set the relation is defined over, Cartesian product with itself. So we know that R is partially ordering. In all cases, how does the cardinality of R relate to the cardinality of X? Okay, so is it greater than, equal to the square of something? Okay, so you have to let me know. Explain your answer step by step, starting with the definition of partially ordering. So what is partially ordered? Okay, reflexive. Okay, so we need it to be reflexive, which is one of the most important part of this relation. Transitive. Okay.
And antisymmetric.
Transitive and anti-symmetric. Okay. All right. Anything else?
Nope.
Nope. That's all. Okay. So out of these three, okay, the empty set or an empty relation satisfies 2 out of these 3 already. Which 2 are we talking about? Transitive and antisymmetric. Okay, so reflexive is the only one that doesn't work with an empty relation. Okay, so if R is, okay, so we can basically say these 2, empty set or an empty relation will work. Okay, but for reflexive to work, we have to define the relation to itself for every element in X. Right? Okay. So for reflexive to work, we need lowercase x. I probably shouldn't use lowercase x, but XX has to be in R for all X in uppercase X. Is that making any sense? So that means the number of elements in uppercase X is the lower bound of the number of elements in relation R. Okay, so the answer is the cardinality of R has to be greater than or equal to the cardinality of X. And that's the best you can say, because you cannot say how much bigger. You can only say that it's at least the same, because if I just define a relation that is just reflexive but not anything else, it would still be partially ordering, because it is still satisfying the requirement of being transitive as well as antisymmetric. So in this particular question, there's no need for you to explain why an empty relation is also transitive and also antisymmetric. You can just kind of say that, an empty relation is transitive and antisymmetric. But it kind of needs to be mentioned so that you can convince me that in addition to all the elements, because of reflexive, there are no additional requirements anymore. Is that okay? All right. So that's number 1. Number 2. So number 2 is asking, given that X is the set of A, B, and C or lowercase, how many ways can we define a function f that maps from X to X? In other words, X is serving both as the domain and also the codomain. Note that the function does not need to be injective or surjective. Explain your answer step by step. So I'm releasing all the extra requirements of being injective or not injective, being surjective or not being surjective. Can be anything. It just has to be a function. Okay, so how many ways can we define a function that maps from a set of ABC to a set of ABC? That is the question. Yep.
We have 3 options. We have 3 things we can map it to. That's 3 to the power 3.
Yep. So the answer is 3 to the power 3, but how would you explain that?
Because there's 3 elements in X, and there's 3 things that it could be mapped to for each one.
Mm-hmm.
And then since it's not injective or surjective, it doesn't matter which order they are. So.
Okay. So what we know is one element has to be A, and then some question mark here, and then B, some question mark here, C, and then the question mark here. We know that f is going to look like this, because this is what you need for a function. Every element in the domain has to be mapped to one and only one thing in the codomain. But since I did not tell you whether the function has to be injective or surjective or not, So you have choices for each one of these. So you can basically say A has options. It can map to A, B, or C. B can map to A, B, or C. C can map to A, B, or C, and they are independent. It's not like if A is already used earlier, I cannot use it later, because there's no requirement to be injective. So the choice of how you map A, B, and C to really place no restriction to the other choices. Is that okay? So that means we have 3 choices here, 3 choices here, and 3 choices here, and because they are independent, so you have to multiply these 3, and it becomes 27. So the answer is 27. So you don't have to explain it exactly this way, as long as the message is clear, that you show to me that A can map to any one of the 3, B can map to any one of the 3, C can map to any one of the 3. You get partial credit just for saying that or indicating that. And then doing the multiplication instead of addition is the other part of the partial credit. Because I'm almost certain that somebody used addition instead of multiplication. Yep.
So if you use like a description to say that because of like you assume 2 cases, I don't know how I explain that, but the third part, like multiplying by 3 the third time, is that for repeating cases, like A maps to A, B maps to A, C maps to A, and all that stuff. Would that be like a good explanation?
I have to read it to actually see what it is like. But the point is basically just that. Okay. So I think I'm going to get answers like 3, 6, 9, and 27. I think those are the possible answers that I'm going to get. The 6 is because of 3 factorial. Okay. So is that okay so far with this one? Okay. So let's move on. And the next one is question number 3. I like question number 3. I know some of you probably did not like that. Okay, so as I was trying to think of a question to ask, doing the dimension folding thing, I was kind of thinking, well, in all the previous exams, I kind of have asked, everything that can be asked using that particular space folding mechanism. And then I cannot remember what else I was doing at the time. I go like, oh, I can do strings with function G. I can basically fold the characters of a string into a single space, into a single line. So I just decided, we'll go with that. And since cisp440 is the co-requisite of this class, it implies that all of you should have taken 400 and 360 already. The first version of this code was using a pointer to a char, and I basically passed str+1 as the parameter. I changed that. I changed that for people who came from more of a Java background because they don't know pointers. They don't know that you can add one to a pointer and it points to the next thing available. So I changed that so that the index is passed explicitly, just so that people who have a background in Java do not feel left out.
You want to make this more complicated than it was?
It is actually more complicated than it is in just regular plain C, but now it is much more language independent. Okay? All right, so the first thing you need to do is to understand encode itself, the function encode. But even if you don't understand recursive subroutines, I do give you an example down here that tag as a string, as a non-terminated string, is going to be G applied to uppercase T, and then the second item of the 2 tuple is the G of A, and then it's all nested like that. The last one, the innermost one, is K, the ASCII code of K and a 0. So that is possible because I give you the quote-unquote theorem at the beginning. Okay, so at the very beginning part, I gave you this part, right? I say if x is greater than 0, non-null, and y is greater than or equal to 0, using the function g, we know that g of xy, g of the pixel xy or the coordinate xy is going to be greater than 1. So that is actually important because this gives you the ability to know when to stop. Because the null terminator itself is encoded in a way that you can, and as you unravel the thing, you can find out, oh, there's the null terminator, it's time to stop. Okay? So that's why the first sentence is actually important, because otherwise you may not be able to find out when to stop. Okay? All right. So to unravel the whole thing is to reverse the order of the encoding. Okay? So when you look at the encoding, when you look at how TAC is encoded, this nesting level, so that means the first time you apply G inversed, you're going to get T, right? The letter T is going to be the X coordinate. And then the second number, the second natural number, is this whole thing here. It's going to be, it's going to be this whole thing from G all the way to here. Is that okay? So you take that number and you reapply G inversed. What is that going to give you? It's going to give you lowercase a and G applied to the coordinate formed by the ASCII code of k, lowercase k, and 0. So when you apply G inverse again, it's going to give you lowercase k and eventually the null terminator. Okay? Then you look at the null terminator itself. Well, since already 0, then you can stop. Because you know that when you apply G inverse to 0, you always get 0, 0 back. So that part won't stop, because you can always apply G inverse to 0. It always gives you the coordinate of 0, 0. Because when you look at how we assign the natural numbers, the coordinate 0, 0 is the one getting the natural number 0 itself. Is that okay? So now that we understand, how G inverse is going to unravel the first, second, and third character, then you have to formulate a code, a program, a subroutine to count the number of characters. Okay, so I don't even need you to store the decoded characters back into a string. I just need you to tell me how long is it. Okay, what is the length of this particular string? So the way to do it, there are multiple ways to do it as usual. And I give you the prototype so that you don't have to think about, okay, what parameter am I given? What is it supposed to return? So that part is already done. And the way to do it is, I would do it recursively. You can do it using a loop. But I just like recursion in this particular case because the coding part, the encode subroutine itself is recursive already. So it kind of makes sense to me to use recursion to count as well. Okay? So the first thing is you have to figure out when you need to stop the recursion. Okay? What type of value of n tells me that it's time to stop? We know the answer right away. Okay? When n equals 0. Okay, so when n equals to 0, we know what it is supposed to return. What do you think it should return in this case? It should return 0, okay? Because when n is 0, we are looking at a null terminator already. So the length of that string, which only consists of a null terminator, is 0. Okay, so you say return 0 here. Yes, I did say that I do not like using return in the middle of a conditional statement, but that's the kind of easier way to write this code. So given limited amount of time, this may not be a bad idea. I'll give you an alternative version later. Okay, what if n is not 0? Well, since n is unsigned, when n does not equal to 0, it has to be greater than 0, right? So when n is greater than 0, that means I can apply G inverse to it. And I gave you this syntax here, okay, right here. So I gave you this syntax to basically say when you apply G inverse to a natural number, it'll give you 2 numbers back. Okay, so to get the 2 numbers back, you basically have to make the left-hand side of the assignment a 2 tuple, and it will just magically put the first item into the 2 tuple and the second item into the second item into the 2 tuple. That syntax actually would work in Perl. That's how Perl can take a list, result and assign it back into another list. Okay. Okay, so in this case, you will need something like that. Okay, so you can say, now since this is pseudo C, if you forget to declare a local variable, it's not a problem. Okay, so I'm not gonna spend time to declare my local variables, but I do want to. Okay, I don't like this pen, but I lost the other one. This one has got a button that I click accidentally. Okay, so I'm gonna call the first one ch for character. And the second one, I'm just going to call it the rest. Okay, and this is the result of applying G inverse to n. Okay, is that okay? And what else do you think I need to do here? I don't really even care about ch, do I? How do I know that this ch is not null? Because it's the else statement. Because n is guaranteed to be non-zero. If n is non-zero, the first coordinate or the x coordinate is guaranteed not to be a zero. Well, I shouldn't say that, but in this case, it's definitely not going to be a zero. Okay. So I can throw away ch. Ch has no particular use of, in my case, but I can do a return right now. Okay. 1 plus. Okay. That 1 is because of ch. Okay, but how many more characters do we have encoded in quote-unquote rest as a variable? Don't ask me. I'm going to call the subroutine again. Ask the next guy. Okay, so this is where the recursion is going to come in handy, because now we can just say, oh, look at the length of the string encoded by the rest. And that's the whole function. Or something like that. You can do it with a loop as well. Okay, you can do it. You can definitely do the whole thing with a loop. If it makes more sense to you to do it in a loop using iterations, use iterations. If it makes more sense to you to use recursion, use recursion. There are no points associated with which one you choose. Is that okay? Now, there's another reason why I like recursion, because I can actually put this into a single line. In other words, this whole function really only needs one single return statement, and this is how we do it. So this is the alternative. I'm going to use a different color. And let's pick blue. There we go. Okay, so the alternative version is a single return statement, but since we do have that conditional thing that we have to take care of, we're going to use ternary operator. Okay, so we say, is n 0? If so, just return a 0. Otherwise, we return, oh darn it, I don't have a way to do the assignment. But wait, in C there's a syntax using the comma, right? So you can have ch rest equal to G inverse applied to n. Okay, I'm counting comma, and then 1 plus length of rest, close paren, and let's see, one more time, there we go, and then a semicolon and a close curly brace. That should do it as well. This comma is the operator. Do you guys know that comma is considered an operator in C as a C expression?
Comma?
Comma. The punctuation comma is actually a C operator.
You cannot override it.
Huh?
You cannot override it though.
You can you? No?
It's advised not to.
I can kind of imagine the trouble you can get into when you override the comma. But comma is actually an operator. Okay, how many people knew that from your C class? Okay, I don't recognize any one of you from my C class because I taught C, once. Okay, yeah. What does it mean? What do you think a comma separated expression means? Or what does it actually return? Okay. I'm going to open a new page just for this discussion. Okay, so let's say you have an expression like this. Expression 1, expression 2, expression 3, and this is, C will actually parse this as if it is just a regular expression. Okay, so now the question is, what is it returning? Whatever expression 3 is, becomes the value of this entire thing. But it does go through expression 1, expression 2, and expression 3. Now in C, we have a very special operator that is not an operator in most other programming languages, the assignment operator. Okay, so expression 1 can use an assignment operation. Expression 2 can use an assignment operator. So the side effect of expression 1 and expression 2 can then be utilized in expression 3. So you can basically do block statements as an expression in C. But it's a very obscure language construct that most people do not use, because most people think about assignment statements as statements only, but not as expressions. But in C, they intentionally make assignment an operator and not a statement, so they can embed stuff like this. But when you use this in an actual C program, you have to be careful, because the optimizer of most compilers would actually optimize a lot of things out of the way, so you may not see the result that you think you should be seeing. Okay, so that's a little bit tricky, but just to show that you can do it in a single line, that's the way to do it. So are there any questions about this particular question? How many people did this in a loop? That's okay. And how many people did it in a recursive subroutine? Fewer. I'm kind of surprised, because to me the recursive version makes more sense, but that's just the way I think. But they're equally legitimate, so that's good. Any other questions? Yep.
So the way I wrote my algorithm, I realized it'd be incorrect for only the 0, but for every other possible n value it would work. So how would you prove that? I basically counted the number of inversions I would have to do, and I realized that if n was already 0, I wouldn't have to do an inversion, but I did it anyways.
So you'd be adding 1 in that case, right?
Mm-hmm.
I haven't decided yet, but I think it's going to be a minor deduction. It won't be a major one. Okay. Any other questions? Any other questions?
Minor is like 0.5 or 1 point. It's 4 points, I assume, right?
Well, with this one, the key concept is you have to apply G inverse to n. And the result has to be utilized in some way. You have to know when to stop. Okay. Now, if you stop one step too far and you count 1 more, it is incorrect, but the key concept is still there. You know when to stop. It's just that you counted it 1 time too many by the time you stop. Okay? So the key concept here is when to stop, how to count, what to do with the inverse applied to n, which basically means whatever you get as the second number, that needs to be, you have to use that in the next iteration. Now, whether you do it recursively like this, or you feed it back to the same loop in the next iteration, same concept, right? You have to utilize whatever the second value is, as long as it is non-zero. So those are the key concepts, and in your case, it is just your counting is off by 1. So I'll give you 1 deduction in one of those things that I'm looking for. Is that okay? All right. Now, of course, the sequencing is also kind of important. If someone just randomly give me, oh, I'm taking the G inverse of something, I'm comparing to 0, and I'm also doing a loop of some kind, but they have it's not structured, it doesn't make sense, the whole thing is just kind of scattered, that would probably get 0 point as well. Yep.
What if you do I was thinking G inverse comma lengths of n minus 1 only, and then
okay, G inverse to Okay, what do you put inside the parentheses?
And then length n minus 1.
Okay,
I
so
don't
that
think
tells
that
me that
works.
you do not understand the G inverse
Yeah, that's
to
what
take
I
a
was-
natural number, because it maps a natural number back to two natural numbers. That's the job of G inverse.
Yeah.
So that would be kind of a crucial concept.
I think I misunderstood the thing.
Okay. All right. Any other issues with this particular question? Okay, moving on. Question number 4. So question number 4 is asking, consider that C, D, E, F are non-empty sets. We define F1 as a function that maps from C to E. We define F2 as a function that maps from D to F. Now we define F3 as a union of F1 and F2. And then in class, I also say, okay, well, for the sake of F3, we consider C union D as its own domain, and we consider E union F as its codomain. So that was not written here, but in class I did write it on the whiteboard. Okay. So the question is F3 guaranteed to be a function? Now that second requirement of what to consider as the domain and the codomain of F3 actually is not needed. You can come up with an example where it doesn't matter how you define the domain and the codomain, F3 is still not a function. Okay, so let me go make an example. There are no further restrictions of how C, D, E, F can relate to each other. They can all be the same, they can all be different. It doesn't matter. Okay, so I just need a single counterexample. Okay, so the answer is no. Okay, so you have to basically tell me a no at this point. Okay, so that you can skip the if so part, and you can skip all the way to if not, right? Because your answer is no. Present an example where the cardinality of all the sets C, D, E, F are greater than or equal to 3 to show that in at least one case F3 as defined is not a function. Be sure to include the definitions of all the sets, including F1 and F2, and explain why F3 is not a function. Okay, so let's go ahead and work on this. So let's say C is ABC, D is also ABC. Okay, we'll define E to be 1, 2, 3. We'll define F also as 1, 2, 3. Okay, there's no restriction saying that you cannot use the same set for multiple of these particular sets. So in this case, F1 can be, okay, just one way to do it, A1, B2, C3. And then F2 can be defined to be A3, B2, and C1. Okay, so now when you look at the union, F3 is F1 union F2. So what kind of elements do you think it's going to have? It's going to have all the elements of coming from one or the other set, right? So it's going to have A1, B2, but B2 only appears once because it is a set. It's going to have C3, but it also is going to have A3 because A3 as a 2-tuple is not the same as A1. So that's why A3 is going to be here. And then the same thing applies to C1 because C1 is a 2-tuple. It is not considered the same as C3. So C1 is going to be here. So when you look at this F3 here, it is not a function. It is not a function regardless of what you consider as the domain or the codomain, because it is mapping A to two different things. It's also mapping C to two different things. So it doesn't even matter what you consider as the domain or the codomain. Okay? So then you can now argue and say F3 maps A to two distinct elements. So F3 cannot be a function. You don't even have to say that you have to map everything to one and only one. You just have to say that it's more than one. It's not a function. Is that okay? All right. Now, obviously, there are many other ways you can define C, D, E, F to make it not a function. This is just one of them. Yep.
Is this kind of the case of C union D being less than E union F?
Has nothing to do with how you do the unions. C union D is the same as C or D, right? Because they're the same set. E union F is the same as E or F because E, F are the same to begin with. But yes, it does have to do with common elements. In other words, if you choose the domains of F1 and F2 to overlap by at least one element, then this type of example will happen. Okay. So do we have any questions about this one? Nobody's asking, how I come up with this counterexample? Really?
I thought of
Makes sense.
Well, when I explain something, it always makes sense, right? Because I have kind of thought this one through already. So the question is, how did I approach this problem? I look at it from the perspective of the definition of a function first. What makes a function a function? One element can only map to one and only one thing in the codomain. So to make it not a function, you can either go for something is not mapped at all, or something is mapped to more than one item in the codomain. Both of those will work. But in this case, eliminating something from the domain, from mapping to something in the codomain, is not likely to work because of the union. The union is always making things bigger, including more items. So if something is already mapped by F1 or F2, it will continue to be mapped in F3. So we have to go the other approach and think of ways so that one thing in the domain of F3 will map to multiple things in the codomain. But that means those two mappings one has to come from F1 and the other one has to come from F2. Okay? But that also means that F1 and F2 must have their domains has to share at least one element, and that element maps to two different things in F1 and F2. So then when you look at the union, now you have the two tuples. Okay, where they map to the same thing to different things. So that's kind of how I construct the counterexample in my head, is to start with the definition. What are we looking for? And given what we have, how do we go step by step to construct it? So other than that as an explanation, I can't really, explain my thinking process any further, as much as I want to. Is that okay? All right, cool. Moving on to question number 5. Okay, so question number 5 is asking, given that f is a function, it maps domain D to codomain E, and this time we know it is injective but not surjective. State in all cases how the cardinality of f relates to the cardinality of D, as well as how the cardinality of f relates to the cardinality of E. Explain your answer, starting with the definitions of injectiveness and surjectiveness. Okay, so the stating part of the definition, you can use the symbolic definition that I have in my notes. You can also just kind of explain it in plain using words. Okay, either way is fine. So in this case, injective means each element in the domain is mapped to a unique element in the codomain. That suffices. Okay, you don't have to use the for all stuff to explain it. surjective means everything in the codomain are mapped to. Okay, something maps to every element in the codomain. Okay, so you can just explain those in words like that. So now getting back to here, we just need to know the cardinality of F. How does it relate to the cardinality of D? And how does the cardinality of F relate to the cardinality of E? But you have to remember that we are already given that F is injective already, but it is not surjective. So those things are what we know already. Okay, the first one is an equality, and that has nothing whatsoever to do with whether F is injective or surjective. It only has to do with F is a function. That's all, right? Because every element in the domain has to map to one and only one thing in the codomain. That tells me that F has to have exactly the same element as in D. The second one is a little bit tricky because we know that the function is already injective, which means there has to be at least the same number of elements in E as there are in F or in D, because F and D have the same cardinality. So we know there's an equal there already. But it cannot be equal to, because if it equals to, it's going to be surjective. So it has to be greater than. Cannot be equal to. Is that okay?
It's the other way around.
Oh, yep. The other way around. Sorry. There we go. Okay, so here's the part where you ask, what if I write less than or equal to, right? Less than or equal to is actually wrong, because less than or equal to implies that equal to is a possibility, and it is not. Yep.
What if you use the subsets instead of equal and greater than? Like F, the cardinality of F is a perfect subset of E.
Like that?
Yeah.
That is a conceptual issue because subset of can only apply to both sides. Each one has to be a set, right?
Yeah.
But in this case, the cardinality of something is a single number. It is not a set, so it's type mismatch from a C compiler. Your program is not compiling. So if your program is not compiling, how am I going to answer the question of is it working correctly?
Test variables? Debugger?
It's not compiling. The debugger is just going to say there's no executable to debug. So that would be, it's going to miss the mark. Okay, so this answer is missing the mark because it is not type correct. But it is not a 0 either, because it does indicate that something is quote unquote smaller, but it's using the wrong relation to indicate it is quote unquote smaller. So in the ABCDF scale, I would give it a somewhere between a C and a D. Probably leaning to the D. But why didn't you choose less than? I'm just curious. I'm not questioning.
Didn't think about it at that moment.
I think I know. Because when you look at the question, when you look at F and E, F itself is a set, right? E itself is a set. So your mind is connecting, oh, we are dealing with the relation between two sets. So you think about, oh, subset of, blah, blah, blah. But you're forgetting that we are taking the cardinality of the sets, which basically means that we're only comparing numbers. So I think that's what's going on, when you chose to use less than a subset of, proper subset of instead of less than. So that might bump your grade back up to a C. Now that I think about why you chose the other operator.
So
Yep.
So by that logic right there, are we allowed to like come back to our exam to say, hey, look, this is what I was thinking. If you see my thought process and see where I'm coming from, if we get something wrong, and my bumper grab in that sense. Just stretch.
I have to come up with that explanation.
Okay.
So you can tell me your line of reasoning, but I may or may not buy it. Yep.
I was thinking, like when looking at the first part of it, where it's the cardinality of f and equal to the cardinality of b. I was thinking of all possible options for the cardinality of f versus just the plain cardinality.
But that means you're not really taking into consideration that we already know that f is injective but not surjective. So we are not looking at all possible cases. We're looking at a very specific case that f is known to be injective but not surjective.
It's injective, it could still have multiple different ways it can be injective.
Well, if it's injective, it has to be less than or equal to. But because it is also not surjective, that locks down the equal to cannot be there. So it has to be less than or equal to. I mean less than, not less than or equal to. Because if I just tell you this part, that f is injective, then the answer is yes. The cardinality of f is less than or equal to the cardinality of e if we know if we just know it's injective.
We're talking about 2D.
2D? That one there's no partial credit for that one, because knowing that f is a function means that if they have to be equal. There's no other way to relate these two. And of course, there's that question of, but Tak, you never mentioned that f is a function. So how do we know it is a function? Because it is injective. Okay, I cannot use the word injective unless it is known to be a function. And the notation also tells you that f is a function, what is the domain, and what is the codomain. All right, question number 6. Okay, let me go back and erase the part that is incorrect. There we go. Oh, too much. There we go. Number 6. Well, I did promise you guys that it will be a sigma notation question, and this is it. And it looks nasty, right? It looks nastier than the one from the previous semester. But in reality, it is not. It's actually easier in a way, right? Okay, so let's see how we can solve this one. Okay, so we're doing a sigma j equals a to b. And then I use extra parentheses just to make sure that people understand how things are nested. This is I going from 0 to j. And we are summing the constant of 1. There we go. Okay. So what do you think this boils down to? If you just kind of expand the whole thing, what do you think it's going to boil down to?
1 plus 1 plus 1 j times.
Okay, j plus 1 times. Because we start with 0. Yep, I know somebody's gonna miss that part. So it's you're gonna get 1 point. That bumps that portion of the grade from a A to a B. But only that portion. Okay, there are multiple portions to your grade for this question. Only that portion gets bumped down. So if you do it step by step, this now becomes 1 plus j. Okay? And does that resemble something that we already know?
And then solid from the previous exams that we had.
Yep. Yep, so the rest you can just copy.
Yeah, I let it put from a previous exam and just put it on there. That's fine.
Yep.
I have time.
Yep. Okay. So do you want me to copy from here, or are you guys getting the idea? Okay, the rest is really the same as the practice exam.
So would it be b minus a plus 1 times 1 plus j? Or a times a plus 1?
Whatever the answer is for the practice exam.
I don't remember.
which you can print and bring with you to the actual exam. But if you don't, we can still work this out, okay, step by step, okay. So we'll work this out step by step, okay. So we say j is from A to B, 1, plus the sigma of j goes from A to B, just j all by itself, okay. So the first one, it becomes B minus A plus 1. The second part, I can change the indexing. So I can say this is going from A minus A to B minus A, and whatever we're adding here is A plus J. Is that okay? So the way I'm doing this is I'm adjusting the indexes to be A less than what they should be, but I'm adding that A back into the expression. So that's why it's still the same value as before. It's just that the way they're expressed is different. Is that okay? So now you get B minus A plus 1, and in this part, okay, this is a plus. J equals 0 to B minus A, and then we have A plus J. So you basically, at this point, you single out the A because it's a constant, and then you have, the other part is just J equals 0 to B minus A, and then you only have J as the summation term. So that one, in return, you can get it from the notes, okay? Because that becomes B minus A times B minus A plus 1, the whole thing divided by 2. The last part. This part, becomes A times B minus A plus 1, because you're adding A to itself, B minus A plus 1 times. So but that part is explained in the previous, in the practice exam already. Is that okay?
So,
yep.
What would is that the closed form?
I run out of space, so let me see if I can continue to work on this. Yeah, I have a little bit more space. I can probably do it here. So the final answer is B minus A plus 1, just this part here, plus A times B minus A plus 1, which is by separating the A in the sigma into its own term, and then plus B minus A times B minus A plus 1, the whole thing divided by 2. So that becomes the answer. You can simplify if you want to, but I don't really need you guys to simplify this. So if you get to this one, it's good enough because it's already quote-unquote closed. There are no sigma in it already. Is that okay? Huh?
I'm not sure if I got this one right, because I had B minus A plus 1 and times A plus 1.
Yeah. So you're factoring out B minus A plus 1 as a common factor. There's a 1 here, right? So 1 plus A or A plus 1, you just factor out that to the other side.
So I just skipped all of this and went right to the closed form. Okay.
Yeah. So that works too. Yep. There are multiple ways to derive this one. So this is just the way that I
it looks a lot
choose
more
to do it.
confusing than what I just.
Does it? Okay. Well, any way you derive it, that makes sense, that is logical and correct, it's going to be fine. Yep. All right. So that's the entire exam. 6 questions. So are there any questions, feedback? Other than a third of the class is not here. No questions? Okay. Yeah, go ahead.
When can we expect to see
At least 1 more week. Yep, at least 1 more week. Yep. So, any other questions? Greater than or equal to 7 days. Or 184 hours. Is that okay? All right? Okay. I'm just going to leave it up here in case anyone has any question. We can go back and answer those questions. And then we are going to continue with our discussion of propositional logic.
Is there any curve?
Yeah, I usually curve it depending on whether there's a need to curve. Okay, so that it requires a little bit of explaining too. So I do curve the scores of my test when it is needed, and typically when it is needed means the top score or the best student in the entire class is getting a B, and there's only one person, and then the rest are getting C, D's, and F's. Okay, so I look at it and go like, no, that cannot be the case. So typically, what I do, especially with a class of sufficient size, is I would curve it to maybe between 40 to 50% of people getting A's and B's, and then the rest will be getting C, D, F's. So that's typically where I hit in terms of the curve, is approximately half the class getting A's and B's, and yep.
Do you do leaf plot curves or what system?
Canvas allows me to drop the lowest n questions, so that is a fair way to do it. Okay, because what you consider to be the hardest question may not be the same as what the other person consider as the hardest question. So I just drop, I would drop the lowest scoring question for everybody, look at the grade distribution, go like, that's about right, then I'll stop there. So that's the only time I do curving. If the whole class answer everything correctly and the entire class is getting A's without adjustments, I'm not going to curve it. Unlike in some 4-year university, they look at the grade and go like, this test must be way too easy, and then they will curve it down so that someone is going to get B's and someone's going to get C's. They may not curve it all the way down to D's and F's, that would not be reasonable, but they would definitely curve it down to somebody's going to get B's and C's. In fact, they have a percentage. I think a lot of professors teaching at a 4-year university, especially UCs, they believe that only a certain percentage of the class should be getting A's. So that's what they're trying to curve to, is in their mind they have a fixed number, okay, like 6.7% or something like that. They would go like, okay, I will curve it so that exactly 6 to 7% of people are getting A's. However the rest works out is however it's going to work out.
Actually, you're right. A bunch of people ace the exam. I mean, I assume some people ace the exam. Some people use C's are pretty smart.
But it's the belief of whether it should be relative or whether it should be absolute, right? So that's a belief thing. Okay, I believe otherwise. I believe that my standard is quote unquote absolute. So if everybody meets my standard of getting an A, hey, the whole class can get an A. On the other hand, I do leave the option open of maybe I tweaked the questions a little bit too hard. Okay, then I'll curve it back up. But in some other people, they can curve it down, thinking that, oh, I made this exam way too easy, and somebody needs to get B's and C's, because otherwise I don't look good anymore. Well, this becomes a yeah. So that's. Just keep in mind that might happen once you move on from here. It may not happen. Okay. All right. So, are we back to propositional logic? Yep. Go ahead.
A quick question. When do you think the grades will come in?
Somebody just asked that question. 183.5 hours now. At least. Okay. But keep in mind that 37.5% is a C. Yep.
Just going back to propositional logic.
Yep.
Remember that that operator kind of.
Mm-hmm.
What is that again?
Entail.
Okay.
Entail. So let me double check and make sure. Okay. So propositional logic entail. It's not a logical consequence. Okay. Images.
No, it's on Wikipedia.
Huh?
It's on Wikipedia.
Okay.
It goes there. It's
There we go. Turnstile is provable from, okay, and they don't use any other name for that. The other one is entails. This one with a double bar is entails.
I think I've also read it as asserts.
Asserts. Yeah, I just look at it as transforms. From whatever you have on the left-hand side, it is syntactically transformable to the right-hand side. Because there are two. Okay, so right now, what we need to remember is propositional logic is a syntactic system. It is not a quote-unquote logic system. Okay, so from our perspective as computer science people, propositional logic or propositional calculus is specifying a syntactic system to basically define what things can you generate out of alpha and out of the omega, out of the operators and out of the alphabet, and of all the things they can generate, what things are true. And we start with iota. Everything, all the well-formed formulae in iota are given to you as true. Okay, don't ask me, but these things are labeled red. Okay, but using the transformation rules, we are basically trying to figure out what else can be labeled red. Okay, so we are using the transformation rules kind of like links to propagate the red color throughout that WFF well-formed formula space until the one point which represents the theorem that you want to prove is labeled. Then we say, we're done. We have a proof. Because then you can follow all the transformation rules leading from everything from the iota to the one point, the one single well-formed formula that you want to prove to be true, and you follow all the links, that becomes your proof. Yep.
So the reason I asked about entails is because like I read like somewhere else that like when you're doing proofs and stuff like that, you're doing kind of like a string of implications from proposition to proposition. So I'm just wondering if you were like doing some sort of proof, like what would be a situation where you would use like entails or something, like as opposed to like an implication or something like that.
Entail or the symbol of T, the twisted T is definitely not implies.
Yeah.
Implication is a logical operator. This is the inverted T or the rotated T is more like a syntactical production.
Okay.
We are basically looking at things without meanings. We are just blindly following the syntactic rules and just say, okay, is this matching? Okay, if this matches, then we go through the syntactic process to extract certain components from what we have to the new well-formed formula that becomes the result of that transformation. It's basically pattern matching. As far as we are concerned, the propositional calculus system is specifying a mechanical way using syntactic transformation to start with certain expressions that we know that we are given to be true, and then we are trying to spread what is true, okay, to other well-formed formula or well-formed formulae until we get to the one that we want to prove. Okay? It in a way it doesn't make sense because it's not logic. Okay, this is actually just mechanical, completely mechanical process. But in another way, it makes perfect sense because this is how computers work. The computer doesn't natively understand conjunction or disjunction or a proof by contradiction or anything like that. It only understands symbols, right? It knows how to compare ASCII characters. It knows how to do all those simple things, but it doesn't really understand what is conjunction, what is disjunction, what is logic in general. It doesn't understand all that stuff. But because we want the computer to do all the work for us, right? So we have to translate what we do with meaning to mechanical operations that the computer can do without the computer actually quote unquote understanding the meaning of logic. Yep.
So what you're saying is that these sort of things, like this syntactical reasoning, like these mechanics, these aren't operations that the computer does, it's the rules that we give it so that it can use.
It models the logic that we are familiar So the propositional logic system is designed so that it by itself it is completely mechanical. It has no understanding of the actual underlying logic whatsoever. But by defining these rules and these symbols, the operators and iota, in a way that is consistent with how we understand logic, then the mechanical system can perform reasoning the same way as quote unquote the same way as we do.
Yeah. Okay.
What we can prove, it can prove as well. That is the whole point. Because we want to mechanize, reasoning so that we can use computers to prove theorems. So that's the context under which we are talking about propositional logic. So from that perspective, it is very different from the discussion of propositional logic in a philosophy class. Because in a philosophy class, you're going back to Socrates and all the other philosophers, where they look at propositional logic as an actual reasoning system for people to use. But in this class, we're looking at this more or less like a mechanical system. Somebody's pissed. Or drunk. The head is on it.
I like
Let me see
probably
it.
12 p.m.
It's 7 o'clock somewhere in the world.
Clear liquid, right? Water. So I'm hoping that I'm getting that message across is why we are studying propositional logic and how it is different from the propositional logic discussion from your other classes. Is that okay? More or less? Okay. All right. So given that discussion, now we need to go back and find, nope, that's 310 stuff. D flip-flop, 310 stuff. Where's my, is that this one? Nope, more flip-flops. Okay. Nope, floating point. Okay, where did I put that tab? Okay, maybe I haven't opened it. There we go. I have not yet opened it. Okay. So one way to kind of envision what we are trying to do is to prove theorems. That's the bottom line. Okay, we want computers to prove theorems for us. To be more specific, the theorem that we want to prove are not the ones that you get from your homework assignments. Okay, we all like to do, have our calculator to do all the proofs for us. Okay, back in the good old days when I took calculus, my calculator is not even programmable. It cannot solve integration or differentiation symbolically. So I have to do all those, manually. Do you guys use scientific calculators to do symbolic proofs with your calculus class?
Not
allowed to. Okay, but you can check, right? When you're doing your homework, when you try to understand the concept, you can go to various websites like Wolfram, Alpha One, and so on and so forth. Those resources were not available to me when I was going through college. So you are lucky. All right, so getting back to this stuff here. Oh, right. So when you envision the whole thing, this is actually easier to draw using the whiteboard, but I can kind of describe what I'm drawing here. So when you look at your alpha and your omega, okay, alpha is your alphabet, omega will be all of your operators. So these combined, okay, will generate a space. So we look at this as a well-formed formula of space, okay? Everything in this space, in this particular set, is valid in terms of syntax. So everything here is syntactically correct, okay? But then we look at all those dots, okay? So there's an infinite number of dots in this entire space. What iota is, okay? Iota is basically saying this well-formed formula, this well-formed formula, this one over here, this one over here, this one over here, and also this one over here. They're known to be true. Don't ask me why, okay? But these well-formed formulae are known to be true. Is that okay? So being quote-unquote true is simply a label, okay? True has no particular meaning other than a label in this sense. Okay? So what about the transformation rules? The transformation rules are represented by, is it zeta? I think so. Okay. So it looks like Z. Let me just double check because I hate to be wrong. Yep. So zeta is representing transformation rules. Now transformation rules are kind of interesting because it's kind of like pattern matching. Okay. Think of it as regular expression for those of you who know what regular expression is. How many people know regular expression, sort of? But it's a way to match things, right? So each transformation rule is specifying a matching rule and say, if you see this particular pattern, extract out the components, and you can rearrange the components like this, and that formula should also be labeled. Okay, I can give you one example. So the example can go back to the tablet. Okay. So I can give you an example. I'm going to use the same workbook here. Let's look at De Morgan's law. Okay, so De Morgan's law says, if you look at the negation of some phi, now phi itself has to be a well-formed formula. Okay, and we say conjunction with psi, and psi has to be a well-formed formula. Okay. So this is a pattern. Okay, I probably should use exclamation point because I'm mixing and matching the operators. But it's a negation. Okay, the exclamation point is a negation. So it's basically saying if you see an expression like this, we have a negation on the outside and we have a conjunction in the inside. Okay, what you have on the two sides of the conjunction does not matter. It becomes a wildcard pattern. Just match that to some well-formed formula. Is that okay? And then this particular symbol means, let's transform that, okay? Let's link it. Let's use this to label something else that will also be read, okay? So what we are linking it to would be the negation of phi or the negation of psi. I mean, that's one side of the De Morgan's law, but I'm only using De Morgan's law as an example. Okay, so it's a pattern matching thing. If one of the red things here that is labeled fits into the pattern to the left-hand side of the rotated T, okay, then we syntactically match it. Okay, you go like, does it fit this pattern? Okay, cool. If something fits the pattern on this side is already labeled red, then we say, oh, this thing should also be labeled red because of this transformation rule. Is that okay? For instance, if in this entire space, okay, I'm going to use black to indicate this one. So let's say we have PQ as one expression. P. Okay, let's make this P or Q. Okay, so P or Q is one expression. And let's say R is all by itself, and then the entire thing is negated. Okay? I mean, if PQR is in alpha, conjunction, disjunction, and negation is in omega, this is legal, right? This is syntactically correct. Cool. Now, for whatever reason, okay, if this thing is already labeled red, okay, because there are some other connections connecting to it, what this particular transformation rule is saying, oh, you know what? In this entire space, there's another well-formed formula that looks like this. Okay, the negation of P or Q and the negation of R. Okay, that transformation rule is saying, let's label this one too. And the way it recognizes that this rule can be applied is recognizing that we can turn this into our phi, we can turn this into our psi. Now it matches the rule itself. Is that okay? You can take a picture if you want to, as long as I'm not in the picture, you can take it. Yep.
So something that has the same meaning but just a different way of
not so much a meaning to it. It is just a blind mechanical application of matching. It's like, okay, do we have something that matches this pattern? Is it the negation of a conjunction?
So it's more pattern based.
It's just pattern matching. Yep.
Shouldn't that be the negation of P or Q and or?
Oh, that's an or. That is correct. Okay, take a picture again once I fix it. Okay, that's supposed to be an or. You're correct. Okay, there we go. Yep.
So the entail symbol there, it's basically saying it ignores any steps that we might have to do to get to our final result. It just says from this starting point, we can eventually get here.
Not even so much eventually. It is just saying if if the right hand side matches, then whatever pattern is on the right hand side, label that one too.
Okay.
So the transformation rules are really just trying to help you spread the color red throughout the well-formed formula space. Because you start with a few dots, right? The few dots are coming from the iota, the set of well-formed formulae that are known to be true. But from that, and by using the transformation rules, you're spreading the red portion out to all the other ones, that should be red. Is that okay?
I think so.
So out of this whole thing, somewhere in this entire space is the one dot, a well-formed formula that is the theorem that you're trying to prove. So now the task to the computer is try to figure out how do I make use of these transformation rules so that this theorem can also be eventually colored red.
Well, I think what I'm asking is,
Mm-hmm.
would it be represented as going from a single iota and then entails that something,
Yep.
entails that? Okay, so it is a longer chain from an original iota.
Possibly. It depends on, whether this is a difficult theorem or a simple one.
Yeah.
So that's the idea.
Okay, that makes sense.
So I think you got the idea.
Yeah.
Yep.
But yeah, so that's like kind of what I was asking about earlier. Like the guy I was like watching was saying that like implies can I guess be a transformation rule because like he was saying that like a proof is just a long series of implied propositions from like P to Q.
Okay. So since you mentioned the word implies,
Yeah,
okay,
that's the same.
it is not the same thing.
Yeah.
So but there's a close relationship between the rotated T and the implication. What makes sense to us, where we can say, oh, this implies that, needs to be represented by a rule that makes use of the rotated T in a syntactic system.
Okay, so that's what we're using.
Yep. But that is no more than a mechanical syntactic way to quote unquote prove theorems. Okay? We are almost running out of time. But one thing, I'm just reestablishing where we left off last time. This space is infinitely large. Okay, because you can say P or not P is true, right? Well, if P or not P is true, then P or not P or the negation of P or not P is also going to be true. And you can just kind of do this as many times as you want, and all of those expressions are going to be labeled red. Are they useful? It is unlikely that you try to prove something like that, right? So you can head in the wrong direction in this entire space and spend eternity exploring and not find the theorem that you're trying to find. So that is the problem with this approach.
So we're trying to devise a way to find the correct chain until we reach the theorem.
That is correct. We want to.
Sure.
Okay. So what we really want is to prove a theorem or disprove a theorem with a limited amount of time. In other words, given a boundary of time, we have to come to a conclusion whether it is a theorem or it is not a theorem. We want to have a conclusion one way or another. This method does not help us, okay? Because this is actually how we prove theorems, right? And you can head in the wrong direction and you can spend an entire weekend on a problem in math or logic and not be able to get it done. So the rest of this module talks about something that seemingly has no relation to what we are currently talking about. It has to do with resolution and CNF, or conjunctive normal form. But those things are basically an alternative version of representing statements that we need to represent. But this particular method, by using resolution, proof by contradiction, and conjunctive normal form, the space itself is no longer infinite. It is now a finite space. And secondly, for each step of the transformation, whatever you end up with is guaranteed to have one term fewer than what you start off with. If you started with like 16 terms, which is terrible, it always ends up with 15 terms. If you started with 15 terms, it ends up with 14 terms, and so on. So using that particular system, because the space itself is finite to begin with, you can put an upper bound of how much time you can possibly spend before you can come to a conclusion. And you will come to a conclusion one way or another. If I tell you something and say, I think this is a theorem, using this method, CNF, resolution, and proof by contradiction, within a known amount of time, you can come to the conclusion and say, yes, it is a theorem, and I can prove it, or it is not a theorem, and I can prove that too. So that's where we are heading in this module, because we want everything to be mechanical, and we want it to be solvable. And that's where we're heading. I guess we'll talk about this next Monday. So over the weekend, just go ahead and read it. If you find something that's really kind of sticky, just kind of skim through it, but keep reading and get the general idea of what the module has to say. Say again? No homework at this point, because we just basically reestablished what we talked about last week.
All right.
Yep. But I felt it was important to do that.
I'm just guessing about this, or kind of just